Chapter 8 is when we really start to deal with rotational motion and rotational dynamics. My picture got cut off. How sad. Um, but we kind of covered that in Chapter 5, but now we're really going to get into um, angular motion, and particularly the last time we dealt with it was with a constant velocity, and now we can accelerate in a circle. So that's the big difference here. All right, angular displacement, some kind of ground rules here. The axis of rotation is the center of what the object rotates around. So the axis of rotation here is generally going to be like so, and then it rotates in a circle around that. Angular displacement is delta theta. So the point from here down to here, that is our, well, actually it's kind of labeled there already, but whatever, I'll draw more. This angular displacement, that's your change in theta. Theta is your angle. Um, Angular displacement is positive if it's counterclockwise and negative if it's clockwise. For some reason, I had a hard time remembering this, so I always tell myself clocks are negative, even to this day. Clocks are negative, so if it rotates in the same direction of a clock, we consider its displacement negative. If it rotates in the opposite direction, we consider it positive. A radian is defined as S, which is your arc length, which I kind of drew here as well. Sorry. Um, Divided by R. We usually write this, and I usually express this as S equals R theta. Um, where S is your linear variable, and then R theta, that's your angular counterpart. And what is the uh, theta? Well, 2 pi r is, let's say you go, okay, let me reverse this. I need to be more clear, fully aware. All right, so let's say I take this and I rotate it all the way around in a complete circle. We know that in a complete circle, you're going to go through one circumference. And so S, losing it right here, that's your arc length, is going to be 2 pi r. And so if you do one complete revolution, we have 2 pi r, r's cancel, and then we have 2 pi radians. So what that means is that, I don't want to do it that way. There are 2 pi radians for every one revolution, or 360 degrees. 2 pi radians. 2 pi is actually a constant. Well, okay. I don't really know how much of it is wishful thinking, but some people will express 2 pi as a constant of tau, which is a Greek letter, because 2 pi is a little bit more sensible than just pi. Since you go in a full circle when you do 2 pi, we do everything in terms of revolutions in this world. But yeah, sometimes you might see that as tau some places, but I don't think it's really pi is more. They're trying to push 2 pi, or sorry, they're trying to push 2 pi as being tau. So those are kind of the things you need to know, at least with the basics of angular motion. Now, what about angular velocity? How basically angular velocity is how fast an object is rotating with respect to time, and this is represented by another Greek letter you haven't seen before, but this is an omega. It's a lowercase. And you make an omega by making like the little W, but you kind of make it wider, so it's like wee wee, and that's your omega. Okay, wee wee. As long as you say that, you'll make your omegas. And so that's going to be your change in theta. So basically, you're changing your angular displacement over time. And likewise, this is very similar to Chapter 2. Instantaneous angular velocity would, if you took the limit at a certain point, you would get delta theta over delta t, or rather, as time approaches zero, gets smaller and smaller, that you would not have an average angular velocity anymore like this one is. This is more of an average. You would have an instantaneous. And we assume most of the time that it's going to be, instantaneous. These equations hold for every particle in the rigid body. What does that mean? Well, let me draw you a picture. This is Earth. This is North America. This is South America. The people in North America go through 360 degrees of rotation every 86,400 seconds per day. People in South America go through 360 degrees of rotation for every 86,400 seconds. People on the South Pole go through the same thing. So everybody experiences the same angular velocity and the same angular displacement. What we don't experience is the linear velocity. People on the equator are traveling faster than people, let's say, in Alaska up here, AK. People in Hawaii will be traveling faster because they're at the equator, so they have a larger circle. But the angular speed and the angular displacement is going to be the same for all parties. So that's every particle in a rigid body. So everybody on that body experiences the same thing. Angular acceleration, same process as kinematics. Your average angular velocity is delta theta over delta t. And we could express it with terms of calculus. But really what you need to know from this is an alpha. It is also easy to make. You just take like one hook and you go wee wee, just like omega, and that's an alpha. It's a lowercase alpha, and that stands for angular acceleration. And so it's the exact same thing. Whereas linear acceleration, your average linear acceleration, if you remember, was your change in velocity over change in time. Well, this is your average angular acceleration. Pretty much the same process as Chapter 2. Now, this is going to lead us to some new equations. Let me look ahead real fast. That I'm going to cover in 2 slides, but I had to check to make sure when I was planning on covering those. So let's start with this problem. Assuming a circular orbit, and I told you our orbit's really not circular, it's more of an ellipse. About how far would the Earth travel from its aphelion, furthest from the Sun, to its perihelion? So what I mean by that is, and I've drawn this out, I think in Chapter 5. So we're assuming that's a nice circle. So basically we want to go from here to here, and the semi-major axis is 1 AU, and that'll be my radius. So I want to figure out how far it would go. We know that S is equal to r theta, and S is what we're looking for, is the actual distance that we traveled, as we travel this way. The radius is going to be 1 AU, so that's going to be 1.5 times 10 to the 11 meters. And the angle. Now, when we do a problem like this, we can't use degrees. We'll have to use radians. So I can't say 180 degrees, but I can say pi radian. Now, multiplying that out gives me 1.5 times 10 to the 11th times pi. Gives me 4.71. We'll just say 4.7. Times 10 to the 11th meters times a radian. But radians aren't true units, so they drop off and we just consider them as meters. And that's kind of the weird part of angular kinematics, is that radians is not a true unit, rotations isn't a true unit. Kind of like with periods, we said cycles per second and cycle wasn't a true unit. Same thing here. Radians is not a true unit, so you just call it meters, not meters radians. Now, I kind of said this earlier, but we do get a bunch of new equations now, but they're all similar to our previous counterparts. What I mean by that is, let's start with the equation we use the most in Chapter 2, which was x equals v naught t plus 1/2 at squared. Becomes theta, or rather delta theta to be more accurate, is equal to omega naught t plus 1/2 of alpha t squared. The v equals v naught plus at becomes omega equals omega naught plus alpha t. V squared equals v naught squared plus 2a delta x becomes omega squared equals omega naught squared plus 2 alpha delta theta. So as you can see, each of the linear equations that we used, and this isn't really all of them, this is just some of the basics, becomes angular. Even something as simple as if we said that x was equal to your average velocity times time, well, this one becomes theta was equal to your average angular velocity times time. You just replace all of your v's with omegas and all of your a's with alphas. Your t's stay the same, and replace all your x's with thetas. And that's it. That's all you got to do. The math is roughly the same. This is one of your easier chapters to do just because it's kind of a rehashing of what you've been doing, except you're only going in a circle. So let's do a problem. All right, a bike wheel is getting trued. This is a truing stand. Do I know how to use it? No. Just whenever I think of angular problems, I think of a truing stand. Apparently, you mess with the spokes and you can realign your rim or something weird. I don't know. I just know I used to see them in bike shops when I was a kid, and so I decided to do a problem on it. It's getting trued, has an angular velocity of 25 radians a second, then 5 seconds later has an angular velocity of negative 12. What's the angular acceleration? How many rotations does it go through? All right, so if I want to figure out angular acceleration, I am given my initial angular velocity, I'm given time, and I'm given my final angular velocity. That's not a final. There we go. And so the equation I'm going to use has all of them in it, and that is omega is equal to omega naught plus alpha t, which is your v equals v naught plus at. So I plug in what I know. This will be negative 12 radians per second equals 25. Yeah, so 25 radians a second plus my angular acceleration, which I don't know. That's what I'm looking for. And then my time of 5 seconds. Okay, so I take my negative 12, and I'm going to subtract 25, and I'm going to divide that by 5. And that's going to give me negative 7.4. And notice this will give you negative 7.4 radians per second, or radians per second squared. So just like meters per second squared, but now we're dealing it with radians per second squared. The acceleration says that it's negative, and it makes sense since it was slowing down. Okay, and what also does this mean? Just to kind of be a little bit more clear. Remember that if it's positive, it's going to move clockwise. So it started off moving clockwise. Ooh, I'm not running out of room right here. But then later on, it was negative, so it was moving counterclockwise. CCW usually stands for counterclockwise. CW for clockwise. Should probably write that out to define it, huh? So we actually know the direction it was rotating, and then we know that since the angular acceleration is negative, it was moving in a counterclockwise direction to slow it down. So based off of the signs, we can see it's not like what direction it's moving forward, it's moving backwards like we did with linear, but it's what direction, clockwise or counterclockwise, it was going. So you can actually pull a lot of information from that. Second part, how many rotations occurs during this time? A lot of different ways we can do this, but I'm going to go ahead and use my theta is equal to omega naught t plus 1/2 of alpha t squared. Theta equals omega naught was 25 radians per second. This occurred over 5 seconds. Plus 1/2 of a negative 7.4 radians per second squared times 5 seconds squared. All right, plugging it in. That gives me 25 times 5 plus 0.5 times a negative 7.4 times a 25 gives me a positive 32.5 radians. But it asks for rotations. And for every 2 pi radians, there occurs 1 rotation. So divide that by 2 pi. .17. We could also say the same thing for revolutions. Excuse me. Okay, so excuse me. Boat motor. So boat motor has initial angular velocity of 200 meters radians a second. Sorry, that's a boat motor, by the way, if you don't know what it is. 13 seconds later, it's now traveling at negative 50. So very similar to the last problem. I need to remember to switch this. How many revolutions occurred during this time? So our initial angular velocity is omega naught. Then this is time. And this is our final omega. And I'll do this slightly different than I did last one. Basically put, we need to figure out theta, but we can't use theta is equal to omega naught t plus 1/2 of alpha t squared because we don't know what alpha. So let's find alpha. So we're going to use omega is equal to omega naught plus alpha t. That's a very bad omega naught. Let's make it a bit better. There we are. So negative 50 radians a second equals 200 radians a second times plus alpha times 13 seconds. So we take negative 50 minus 200, so that's negative 250, and divide that by 13. That's going to give me negative 19.2. Radians per second squared. I'm going to do it slightly different. This time, since we know we can use the omega squared is equal to omega naught squared plus 2 alpha delta theta, we can use that one to solve for theta. Let's do that. So take my omega squared, subtract omega naught squared, and divide that by 2 alpha. And that's going to be delta theta. And so final final velocity squared. So that'll be a negative 50 radians per second squared minus the initial of 200 radians per second squared divided by 2 times negative 19.2 radians per second squared. All right, so negative 50 squared is going to be 20 that's weird, that's not right, but negative 50 squared is going to be 2500, and I'm going to subtract 200 squared and then divide that by 2 and then divide that by negative 19.2 is going to give me a positive 976.6. That's also in radians. Revolutions is pretty much the same thing as we did last time. There are 2 pi radians for every revolution. Revolution and rotation are essentially the same thing. So I'm going to take that number and I'm going to divide that by 2 pi, and that gives me 155, roughly. The reason I'm doing this is because a lot of times we don't express things in radians. When they're talking about the something spinning in RPMs, they're not talking about radians per minute, they're talking about revolutions. That's generally how we care about. So, or what we care about. So we have to use this in order to get to that point that we can figure out the revolutions. Okay. Linear and angular variables. While your angular velocity is the same for all objects rotating around a fixed axis, as I mentioned earlier, the linear speed, as I also mentioned earlier, is not. We know that linear speed from chapter 5 is v is equal to 2 pi r over t. So the bigger your radius, right here, the higher the linear velocity, which means that the more, closer you are to the equator where you circle in larger, you're going to have a higher linear velocity. We can actually relate our linear and angular velocity variables, and we can figure out our tangential velocity, and that's nothing more than the radius times the angular velocity, which makes sense. Radius is measured in meters. Angular velocity is measured in radians per second. That gives you a meter radian per second. Radians isn't a true unit, so you get a unit of meters a second. So the units end up working out. This is very similar to S is equal to R theta. Note the pattern, because we're going to see this one more time. But this gives you the tangential velocity. And once again, the tangential velocity is the velocity at a point measured on the rim. And so that point on the rim is going to have a different tangential velocity than some object roughly right here closer to the center. So the further out you are, the higher the tangential velocity. That is going to lead into angular and angular acceleration. So basically, we know that tangential acceleration, that's literally what we were dealing with in chapter 2 and 3. In the definition of an acceleration here is some velocity minus the initial velocity over time. So I just put them in with respect to tangential, so the final or instantaneous tangential velocity, initial instantaneous tangential velocity divided by t. And we know from earlier that that's equal to r omega. So subbing in r omega naught. Pull out your r, and that gives you delta omega over delta, gives you delta omega over t. And what's that? Well, that is nothing more than your angular acceleration. You're changing angular speed over the change in time. And so now we have AT equals R alpha, VT equals R omega, and S, well, there's no T on that one for some strange reason, there just never has been, is R theta. So all three variables that we were talking about. So you just slap on an R, and you can just literally change it right back to its linear counterpart. Now, there are... Sorry, my throat's bothering me. There are situations where you may want to figure out, say, your centripetal acceleration. Well, we remember from chapter 5 that centripetal acceleration is a velocity over r. But if we're going in a circle, we use the tangential velocity over r. And we know that that's r omega squared. So this is r squared. One of your r's stays. This r goes away. And now we get a slightly different formula, but your centripetal acceleration is r omega squared, not to be confused with your angular acceleration, which is r omega, as we saw from earlier, or r alpha. Yeah. Sorry, that's right. AT here. I don't know what I was doing. That's why I rolled up to the top real fast. So r omega squared gives you your centripetal acceleration. You will, if you're rotating in a circle, you're going to have centripetal acceleration. Whether you're speeding up or at a constant speed, there's going to be centripetal acceleration. You can use that by finding r omega squared. So now we can actually have two accelerations. So if we're rotating in a circle, we will have our tangential at some point, AT, and we will have our inner AC. And so we could figure out the overall acceleration by using, like, Pythagorean theorem or something similar to that to figure out our total acceleration, which isn't going to be up this way, isn't going to be that, it's going to be somewhere right along here. So we have multiple different accelerations going on. So two different accelerations, that's kind of the new thing here. I want to erase that for some reason. That's good. This one's harder to do. Oh man, I haven't even thought about this. Angular versus vectors. Angular velocity points in the direction that the right-hand rule guides you. What is the right-hand rule? Well, just like this little picture is, you take your right hand, and if you curl your fingers in the direction of the rotation, you will see the direction of the angular velocity vector. So, let's say we're going this way. You would curl your fingers in the direction, and so the angular velocity vector it points towards you. Let's say we rotated this way. Your angular velocity vector, oh, didn't spell velocity right. I did the exact same way. There. Points, well, in this case, in the computer. So it's pretty simple. This doesn't have a lot of importance in Physics 1, but in Physics 2 it definitely does when you have to find the direction of your magnetic field vector and the direction of your electric field. So it's best to kind of get an idea of how this works in Physics 1. But it's called the right-hand rule. You cannot use your left hand. You must use your right hand. Your thumb will always point in the direction of that angular velocity vector. Because these values are vectors. They do have magnitude and direction. So we had to figure out the direction of said vector. And it points up at a 90-degree angle from the direction of the rotation. Okay, so we'll do a problem about relating linear and angular variables. Every year I say to myself I'm going to cut this problem because most of hard drives are now SSD, solid-state drives. Solid-state drives do not use spinning platters and things like that. However, a lot of your backup drives, NAS drives, they actually are traditional hard drives. And a reason I kept this is because I think it was Western Digital got in trouble because some of their hard drives that people bought at 5,400 RPM, I believe was the number, were actually spinning at 7,200 RPM, which most people were like, hey, if it's spinning faster, that means I can write data faster. And yeah, why wouldn't I do that? Well, problem is some people bought those specifically because of the low power requirements. The faster it spins, the more energy it needs, and they may not need them to spin that fast because you have a ton of backup drives that could actually drive up your energy costs. And so Western Digital, who usually makes a lot of hard drives, is kind of pissy about that. But anyhow, it's still making news, at least in my world, so I decided to keep it. So we got a computer hard drive platter, rotates to 7,200 RPM. That's roughly the higher number for most hard drives, at least traditional ones. We need to figure out the angular velocity of the platter. The reading, the reading head is 3 centimeters from the spindle, and the reading head is right there. What's the linear speed of a point on the platter below it? And a single bit requires 4 nanometers of length. How many bits per second can the writing head write? So, let's start with the first one. What is the angular velocity of the platter? So we need to convert 7,200 RPMs backwards. So that's 7,200, say, revolutions per minute. And let's get it to revolutions per second. So for every 1 minute, there are 60 seconds. And let's get that from revolutions to radians. So for every 1 revolution, there are 2 pi radians. There we go. So I take 7,200, divide that by 60, multiply that by 2, and pi. And I get 700, and we'll just go around it, 754 radians a second. All right. So that is our angular velocity. It's actually our average. So I want to write W average, or omega average. It says the reading head is 3 centimeters from the spindle. So that's this reading head down here. We're assuming that this little distance is 3 centimeters. We want to know the linear speed of a point on the platter below it. So from earlier, we discussed that our tangential speed, which is the same as linear speed, was equal to r omega. So I could take my radius, 0.03 meters, because we got to express that in meters, times my 754 radians per second. And so I take that big number and multiply by 0.03, and I still get 22.6 meters a second. I mean, that's still, 45, 50 miles an hour. Because once again, remember, radians is not a true unit. So that gives me my tangential speed. And then if it's like at the edge of the spindle, I would have to take the radius of the whole spindle and so forth and so forth. What about this? A single bit requires 4 nanometers per length. How many bits per second can the writing head write? Okay, so it's saying that a single bit, so 1 bit, is going to require 4 nanometers. What is a nanometer? That's actually going to be 4 times 10 to the negative 9th meters. Just to kind of give you an idea, coming up here, where do I go? There are 1 times 10 to the negative 9th meters is equal to 1 nanometer. And you'll deal with this a lot more in physics too. So that's bits per meter, right? And we want bits per second. Well, I know that it can move at 22.6 meters for every second. That would cancel out my meters and leave me with bits over seconds, which is what I want. Do that. So 22.6 divided by 4 times 10 to the negative 9th gives me an absolutely huge number. Let's see here. That gives me, oh God. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, 8, 9. So 56. Oops. Ah. Come on, help me erase here. There we go. So it looks like it's going to be 56 times 10 to the 9th bits per second. So I said 56 times 10 to the 9th, or I could say 5.6 times 10 to the 10th. Either one will work. I'm going to keep it like this because when we get to later chapters, they express a lot of things in terms of, like, they don't do scientific notation as, 3.2. It'll be like 32 times 10 to the something. So that gives me bits per second. If I wanted to figure out, say, bytes per second, kind of go a little bit further, there are 8 bits in 1 byte, because if you look at how your files are saved, they're generally, expressed in bytes. So what I can do is take my 56 times 10 to the 9th bits per second, and I know that for every byte there will be 8 bits. So I divide that by 8, and I get, looks like 2, 3, 1, 2, 3, 1, 2, 3. Okay, that's going to give me 7.1 times 10 to the 8 bytes a second. And then most things are expressed in terms of, say, megabytes. And so if I wanted to do it in megabytes, I would just divide that, and I would have like a really high number of megabytes per second. But I just wanted to show you what this is in bytes per second, just because bytes are generally what we deal with. And this is a really high number. I think I changed it to 4 nanometers, and I probably should have kept it in the micrometers, but it is what it is. All right. So there's that problem. I decided to add this one because there's a problem in your homework like it. Assume that you got like an Atwood's machine. Although we're not actually going to solve like an Atwood's machine, as I'll tell you. The bucket on the right, the picture below. Sorry, assume the bucket on the right and the picture below falls from rest and strikes the ground 8 seconds later. If the pulley has a radius of 10 centimeters, we want to know how many revolutions will the pulley have, what's the angular acceleration of the pulley, and what's the angular speed, final angular speed of the pulley. And I give myself room. Thank you, me. Okay. So, all right. What do we know here? We know that it hits the ground 8 seconds later and it starts from rest. So there's a couple different ways I want to do this. But really what I want to do, I think the easiest way to approach this problem is I want to figure out how far y it would fall. We know that the initial velocity was 0. We know the time is 0.8 seconds. And it's in free fall, so this is back again to having the acceleration being negative 9.8. Okay, so I know enough information to find out the displacement y, so that's what I'm going to do first. So y is equal to v naught t plus 1/2 of at squared, or y is equal to 0 minus 1/2 of 9.8 meters a second squared, 0.8 seconds squared. Plugging that in my calculator, 0.5 times 9.8 times 0.8 squared is going to give me 3.1. Negative 3.1. But we know it's going to be displaced by a linear movement of 3.1. And I will need that later on. So that's my first step. Now, going back to the previous problem, we know the pulley has a radius of 10 centimeters. We want to know how many revolutions does the pulley have. So how does this relate? Well, the reason I did this is because I know that S is equal to R theta. And S is, it's going to rotate, or it's going to go through as many rotations as the length of rope that's going to drop in 0.8 seconds. And so we know that S is equal to the 3.1 meters. We know the radius of the pulley is 10 centimeters, or 0.1 meter. And so we can use this to figure out theta. So let's do that. 3.1 meters equals 0.1 meters times theta. So 31 radians, remember because it's not a true unit, is equal to theta. That doesn't give me revolutions, but that does give me radians. So now I need to figure out revolutions. How do I do that? Well, let's come back up here. We take my 31 radians, and I know that for every 1 revolution, there are 2 pi radians. So I'm going to divide 31 and divide that by 6.28. Well, close enough. And that gives me around 5. Just go around at 5. And man, I chose that problem to an exact answer. All right, so 5 revolutions the pulley will go through. So we know that now. Now we want to figure out, well, what's the angular acceleration of the pulley? Okay, couple different ways that we can do this. I think our easiest way is our theta equation. Theta is equal to omega naught t plus 1/2 of alpha t squared. We know that theta is 31 radians. We know omega naught is 0 because it was originally started from rest. We know our now time, so we have enough information to solve this. So let's do that. 31 radians equals 1/2. Oh, this is really easy, but there's a much easier way of doing it. We're going to solve it this way because I already started it. I'll show you both ways. I don't know why I didn't. I just get brain fart, I guess. 0.8 seconds squared. We should get roughly a value, so this would be a good way of checking it. So 31 times 2, divide that by 0.8 seconds squared. It's going to give me an appropriate value of 96.9 radians per second squared. And then another way of doing this is just to find your AT is equal to alpha R, and then you can plug in 9.8 and then divide that by R of 0.1, and you'd get something similar, but the values are slightly off due to rounding. That would have been a much easier way of doing this, which I originally intended to, but I kind of forgot when I was going through it. I'm like, oh well. Anywho, that will give you angular acceleration, but we'll use this one since I started off with it, and it's, like I said, due to rounding, it gives you a slightly different value than the 98 radians per second squared. Final angular speed, we're going to use omega is equal to omega naught plus alpha t. This is 0, so omega is equal to 96.9 radians a second squared, 0.8 seconds. So 96.9 times 0.8, and that gives you roughly 77.5. So all sorts of different things I can come up with based off of this little bucket situation and 2 little buckets. And I left myself room, but apparently I guess I didn't need it. The last example kind of comes out really crappy, but let me do this real fast while I have you captivated. Captive audience, there we go. I'm kind of find a better picture real fast. That works. All right, so take a look at this picture. Come on. Oh, it's a video. Oh, wow, it's really long. Okay, I don't want to do that. I don't want to see this man. Go away, man. Go away, man. I just want your picture. Okay. Notice a couple things about a wheel. Like you've noticed it before when you see a bike wheel or anything rotating. You'll notice that the top will be blurry while the bottom you can actually make out the individual spokes. And there is a reason for that, a mathematical reason for that. And you can kind of see it in this picture, but it came out really crappy and that makes me sad. But basically, there are multiple different things going on. You have 3 different, 2 different things. We've talked about rotational motion. That's this chapter. And we've talked about translational, which is the same thing as tangential. So when an object is rotated and moving, we actually have to tangential. We have to factor in both the translation and the rotation. And so if we just look at this object over here as pure rotation, and you look at 2 points on the wheel, one at the top, one at the bottom, the object rotates, look like this direction, so it's going to rotate in a clockwise pattern. And the point at the top is going to move to the right, and the point at the bottom will move to the left, just because that's the way it's going to look, based off of just rotation. So it's not moving left and right, we're just looking at the object rotating. And so, couple things here. The velocity of the center of mass is moving in this direction, and it doesn't talk about that, but it is. So we know that the velocity of center of mass is moving this direction. So the velocity at the top is going to be equal to the velocity of the center of mass, whereas the velocity at the bottom is going to be the negative of the velocity of the center of mass, due to the rotational. Now, if you look at translational, you've got the velocity is going to be the same as the center of mass at the top, the bottom, and the middle, because the whole, we don't look at the object rotating, we look at just the whole wheel itself as if it was stationary. And so what we can do is we can put that together. Well, we've got the velocity of center of mass is moving right, plus the velocity of center of mass is moving right here, and that gives me twice the velocity of the center of mass. Then the negative is going to cancel with the positive to be 0. So what that means is that objects on the top of the wheel are actually moving, little points there, twice as fast as at the bottom of the wheel. And remember, this only works for objects that, it's what's called rolling motion, and objects that are both rotating and have translational or tangential speed. And so that's why you see the spokes of a tire probably on the bottom, but see a blur to the top. And that's due to the combination of translational and rotational motion. And with that, that is the end of this chapter. As I promised, it's a pretty easy chapter. I'll try to clean up these pictures when I actually post it. At least I was able to find one online. And then we'll start chapter 9 soon. Fun.